slide. Oops, I messed up. All right, now I have to scroll through and find where we were. I didn't see the K. We're on the factor theorem. That's where we start today. Before we get started, any questions from anything we've done so far? Okay. Let me do a couple of reminders here. We're rapidly approaching the end of the term. In this class, I would say fewer than half the people have turned in your research papers. It's probably the most of any of my classes, but still more than half of you have not turned it in. Just barely more than half, or a little, maybe 2/3, have turned in the first quiz. I need your first quiz. And of course, if you haven't done your first quiz, you couldn't have done the first test. So all those who haven't turned in their first quiz haven't done the first test, and some that have turned in the first quiz haven't finished the first test. And you got the second quiz now, so please, folks, we're running short of term. Here you are doing the second quiz, and you haven't turned in the first quiz yet. Yes?
You got the first quiz?
What's that?
Do you have another copy of the first quiz?
I may. I only make enough for the people that are in the class, so only if someone hasn't shown up would I have that. Nope, I'll have to make you a copy, but if you wait after class, I can run down and make one. Okay, you need more graph paper for that one too?
No.
You don't? Because there is graphing on it.
Yeah, no.
Okay, well, I'll have to make it after class, because I gave out all those, so I imagine you got one. Okay, all right. Okay. Any other questions before we get started? Okay, now we talked last time about the remainder theorem. Someone remind me what the remainder theorem says. It's pretty interesting. Uh-oh. I know it was 5 days ago. I mean, it's a long time, okay? What was the remainder theorem? Okay, number one, you have to have a situation that you can use synthetic division. In other words, you're dividing by x minus k, where k can be either positive or negative, but it's x minus k. Now, if you do that, and whether you do long division or synthetic division, but you have a factor or a divisor that is x minus k, when you do that, if you come up with a remainder, if there's a remainder, that means that f of k is that remainder. So it's another way of evaluating a function. Rather than plugging in, raising it to powers, and adding and subtracting and doing all that, just do simple synthetic division, which is all multiplying and adding. No raising to powers at all. And pretty simple process, and you can come up with what f of k is. That was a remainder theorem. Another important theorem that sort of relates to that is the factor theorem. Okay? A polynomial f of x, that would be your divisor, okay? I mean the dividend, has a factor f minus k if and only if f of k is equal to 0. Okay? Now, let's think again. The remainder theorem said that if you're divided by x minus k, f of k is your function value. Well, if f of k is 0, that means the remainder was 0. And that meant that that was a factor. Okay? So this is actually stating something we already knew. That x minus k must be a factor of that f of x, that dividend. Okay? So using the factor theorem, you can test whether a polynomial has x minus k as a factor by evaluating the polynomial x equal k. Okay? Now, quite often it's easier to do synthetic division, but sometimes it's easier to just plug in and evaluate. If the result is 0, if x equal k gives you the function equals 0, then x minus k, remember if x equals k, subtract k from both sides, that would be a fraction. Okay? So, this is helpful in at least two circumstances, one of which we're going to be doing a lot of in the next section or two. Actually, maybe 2.5, which is the one with complex numbers. Whichever is the section with complex numbers, we're going to just hit the high points and move right quickly through that. All right, so let's do example 6. Now, example 6 is a really simple one, in a sense, because they've already said these are factors, okay? We don't know whether to believe them or not, but they say they're factors, okay? And it says show that they are, okay? And then find the remaining factors of f of x, okay? Now, there's two ways to show these are factors. Can anyone name those two ways? One of the ways to show that's a factor. I don't know how to factor fourth degree polynomials. Okay? That's daily woo. 1, 2, 3, 4, 5 terms. You can't do factoring by grouping because it's an odd number of terms. That's, I don't know how to factor that. So how can you show that those two are factors of it? Okay? Here's Chris. Is anyone else come in since I called up? Two ways you can show those are factors. Okay. Divide, exactly. What would you divide? There's two ways you can divide. What would you divide? Say again? Long division you certainly can do. You can do x minus 2 outside, do this inside the house, and do your division. If you're a hard worker. Okay? If you're a little lazier, what might you choose? Synthetic division. Then what goes outside the house? 2. Not minus 2, 2. And then you just put your coefficients down. Okay? But you have to remember to include every term. This one's not missing any terms, so you're fine. And use the synthetic division. What will let you know that's a factor when you do your synthetic division? Second? Remainder is? 0. Fantastic. Remainder is 0. Okay? Second, the other way is to plug in x equal to into this, raise it to those powers, multiply it, add it, subtract it, and see what you get. To me, that's the long way. If you get 0, it's a factor. This is a factor. If you don't get 0, it's not a factor. Now, which of those two ways do you want to use? 3 ways. Long division, synthetic division, or plugging in. You tell me. Say again? I was hoping you said that. Okay. So, what do we do for synthetic division? What goes outside the house? 2. Let me get my pen. Okay, there we go. 2, and what goes, goodness, this is so slow today. Okay, what goes inside the house or wherever? 2, 7, say again? Negative 4, negative 27, negative 18. Now, what's my little suggestion to you? You should have done this beforehand. Make sure that your powers are in descending order. 4, 3, 2, 1, 0, blast off, okay? Yes, they're in right shape, okay? Number 2, and this goes with that, count the number of coefficients. 1, 2, 3, 4, 5. One more than the 4 here, maximum the degree. Yes, you've got the right number. And if those are in descending order of powers, you have them in the right order. All right, what's my next little rule? Anyone remember? I know it's been a long time. Skip a line, draw a line. Skip a line, draw a line. Okay, that's my little rule. You'll never see that in the book. And then what? Bring down to 2. And then? Multiply. And what does that give you? And then? Say again? You do what with 7? You add. And what does that give you? 11. Okay, next. Multiply. This is not looking good, is it? What does that give you? 22. And then? And that gives you 18. Pretty big numbers. Then? And what do you get? 36. Ooh, big numbers. And then? And what you get? Ooh, they finally started decreasing. And then? And what you get? And that gives you 0. Right, what we're looking for. So you've just shown that x minus 2, well, you've shown two things. X equal to is a solution to that, if you set it equal to 0, and x minus 2 is a factor of that. Okay, good deal. How about the next one? How do we show that x plus 3 is a factor? 3 ways. Second? Long division. Synthetic division. Or plugging in. What would you plug in? Not 3. Negative 3. X equals negative 3 there. Then you raise it to all those powers and stuff. I don't want to do that. Okay? So what do you want me to go to? Synthetic division. Now, do you have to go back to this and divide? No. Because if this is a factor, if it's a factor of this, it will also be a factor of this. Because what does this represent? A polynomial. This is your quotient. There's your remainder. Your quotient, and that would be 2. What do we take out here? Yeah, 2x to the third plus 11 x squared plus 18x plus 9. Yeah, that is your, represents a polynomial. A third degree polynomial because you got 4 terms. Now, we haven't gotten there yet, but I'm going to give you a little heads up. Because all these numbers down here are positive, you will not find another positive factor or a solution greater than 2. But this is a negative one, x equals negative 3. So therefore, we can take this and just divide. Synthetic division, what will you put outside the house? Negative 3, and then skip a line, draw a line. Say again?
4.
Why are you saying 4? Bring down the 2, and then multiply, and that gives you negative 6. Add, and that gives you 5. Multiply, and that gives you negative 15. And that gives you 3. And you get negative 9. 0. Ding, ding, ding. We have another winner. Okay? A winner. Okay? That shows that 2 things. X equals negative 3 is a solution to that, if you set it equal to 0, and x plus 3 is a factor of that and of this. Okay? So you have now shown that both of those are factors. Okay? Using just synthetic division, multiplying and adding. That's all you did. Okay? Real simple process. But then it says, then find the remaining factors of f of x. Could it have any more? How many possible factors could that original problem have? So there is here. If I can find it. There you go. Okay. How many possible factors could that have?
9.
Huh?
The first one?
Yeah. 4. Remember, it can have up to 4 zeros. That means it could have up to 4 factors. We found 2 of them. There's potentially 2 more. You don't have to have any more. Potentially 2 more out there. How would we find those? Hint. this represent? Say again? That represents a polynomial, which is the quotient after you've done these two divisions, right? So tell me what that polynomial would be. A little louder. 2x squared plus 5x plus 3. And guess what you can do with that? Factor it. Why not? Okay. Set it equal to 0, because if it's going to be a 0, then the factors will be here. So how could we possibly factor that? Okay. What's the only possible factorization for 2x squared? 2x times x. Very good. Where do we look next? Sign of the last term, and that's positive. What does that tell you about these two signs? Well, they have to be the same. That's all it tells you until you look to the middle sign and it's positive, and that tells you it does have to be, they both have to be positive. And then what do we do? Where do we look next? Only possible factorization of 3. And what would that be? 1 and 3. Maybe not in that order, but 1 and 3. How do we know whether we got it right or not? FOIL it and see if we get what we started with. 2x times x? 2x squared. Yes, so far so good. 2x times 3? 6x plus x is 6x plus x? 7x? Wrong. So if you come up with the wrong number, what do? Change the numbers. So reverse these and make this one the 3 and that one the 1 and see if that helps any. Now if you come up with just the wrong sign, what might you do? Change the sign. This one doesn't have any sign changes, but oh yeah, it would. Minus minus, that might work. Okay? Let's see if this works. 2x times x? Yes, we already did that one. Outers would be 2x. Inners would be plus 3x. 5x, yes, yes, and 3 times 1 is 3. Yes, we factored it completely. And, well, find the remaining factors. There they are. Okay. Anyone want to tell me the remaining zeros for the function? 1 0 is not negative. X equal 2. If you set that equal 0, then add 2 to both sides. X equal 2. X equal negative 3. Right? And this one. Negative 3 halves. Perfect. Okay. Excellent. Way to go. Now, could you have started your synthetic division with this one? If they hadn't given you the other two? Yeah, no problem. Could you have started with this one? Say again? Why not? Yes, to do synthetic division, you have to have a coefficient of 1 and an exponent of 1. This has a coefficient of 2. You cannot start your synthetic division with the 2. With that. Any of the other 3, yeah, you could have. Hopefully, you'll get it down to the quadratic. Once you get 3 terms down here, stop synthetic division and then factor this using foiling, unfoiling, okay? Whatever, okay? You know how to factor quadratics if they're factorable. And if they're not factorable, you can use what? To get the zeros. Oh, the name starts with quadratic. Formula, of course, okay. So, that's how we did it. Let's see how they do it. Anyone need this up there a little bit longer? Okay. Uses synthetic division for the factor x equals negative 2. They chose the same option you did. Good for you. Good for them. They put 2 on the outside, and they block the other way. you can block it any way you want to. I like doing like this, because then at the end I like doing like that, and it sort of makes it somewhat symmetrical. This is something else. Okay, so you put 2 on the outside, because x minus 2 would be equivalent to x equal to, okay? And put the coefficients inside, making sure that you account for every term and that they're in descending order of the powers. Yep, got it. And then skip a line, draw a line. They do this thing, whatever. Okay, bring down the 2, then multiply and add. 2 times 2 is 4. 7 plus 4 is 11. 2 times 11 is 22. Negative 4 plus 22 is 18. 2 times 18 is 36. Negative 27 plus 36 is 9. 2 times 9 is 18. 18 minus 18 is 0. Ding, ding, ding. Good. You found a 0. X equals 2 is a 0 for the function. And x minus 2 is a factor of that polynomial. Okay? So if the remainder is 0, it is a solution. And x minus 2 is a factor. Okay. Now, from there, you can just continue and check out the x plus 3. So you think x plus 3 is a factor, you put a negative 3 on the outside, because x equal negative 3 would be a solution. Put it on the outside, skip a line, draw a line, and just use the quotient. That's all you need to use. You don't need to use the whole original, okay? Because using the quotient will get you down here where you need to be to get the remainder. To get the last factorization. Again, skip a line, draw a line, bring down the 2. Negative 3 times 2 is negative 6. 11 minus 6 is 5. Negative 3 times 5 is negative 15. 18 minus 15 is 3. Negative 3 times positive 3 is negative 9. 9 minus 9 is 0. Got another solution, x equal negative 3. Got another remainder, factor x plus 3. Okay? And what's more, you're down to 3 terms in your quotient. That means it's a quadratic. And it also means CJ is here. Okay? If I can find you, there you are. All right. And once you get that written as a quadratic, see if you can factor. If you can factor, that will give you the last 2 factors. If you can't factor, use the quadratic formula on it. It'll give you 2 solutions, whether they're factors or not. Okay? Technically, they will be factors, but they may have radicals and other weird things that you wouldn't be able to factor normally. Okay? So they take it the next step, set that equal to, they factor that. What? Okay. Yeah. You're not setting it equal to 0 because you're not looking for zeros, you're looking for factors. So just factor that. 2x squared plus 5x plus 3 is indeed 2x plus 3 times x plus 1. And then the complete factorization would be your x minus 2 from the beginning, x plus 3 from there, 2x plus 3 from there, and x plus 1 from there. See how it works? You factored it completely, even though we had no tool to factor fourth degree polynomials. None whatsoever except synthetic division. Sure, they gave you the first 2 factors. That made it easy. So what we're going to be doing from now on in the next section is coming up with ways so we have possibilities to use as those first factors. So that's what we're going to do next. Okay, that was example 6. There is a checkpoint. I would say as soon as you're out of class and have any opportunity to do your checkpoint. All right? Let's take a look at the vocabulary at the top of page 142. 2 forms of the division algorithm are shown below. Identify and name each term or function. Okay? Okay, what is f of x called? In terms of naming the parts of a division problem. The dividend. D of x. Divisor. Q of x. Quotient. R of x. Remainder. Same thing for that one too. Identify and label each term or function. Okay, number 2. In the division algorithm, which we just saw, the rational expression R of x divided by D of x is blank, because the degree of R of x, that's the remainder, is less than the degree of D of x. What do we call it when the degree of your numerator is less than the degree of the denominator? What kind of, how would you characterize that ratio? Proper, excellent, okay? Improper would be if the remainder was the same or greater degree from the divisor, then you just keep dividing. You don't stop because it's not a remainder. Number 3, in the division algorithm, the rational expression f of x divided by d of x is blank because the degree of f of x is greater than or equal to the degree of d of x. Improper, very good. Number 4, a shortcut for long division of a polynomial is blank blank. Synthetic division, in which the divisor must be of the form x minus k. In other words, coefficient 1, exponent 1. Okay? Number 5, the blank theorem states that a polynomial f of x has a factor f minus k if and only if f of k is equal to 0. A factor theorem, and the blank theorem states that if a polynomial function, polynomial f of x is divided by x minus k, then the remainder is f of k. That's what? Remainder theorem. Perfect. Homework exercises. Do number 7. You'll find the answer in the back of the book, and you'll also find it on calcchat.com. Do number 9. Same deal. Okay? And then do any of the odds 11 through 23. You'll find all those answers in the back of the book. You'll find them worked out at calcchat.com, and you can find number 19 described pretty fully at calcview.com. Okay? Then do any of the odds 25 through 43. And again, all the odds have the answers in the back. They're worked out at calcchat.com. And 27 is worked out at calcview.com with a lot more, it's more interactive. Then do any of the odds 45 to 49. They're all answers in the back and at calcchat. Okay? Then do either 51 or 53 or both. They both have answers in the back. They're worked out at calcchat, and 51 is explained really fully at calcview. Then do any of the odds 55 to 61. They're all answers in the back at in the back of the book and worked out at calcchat. None of those are at calcview. Then do any of the odds 63 to 69. The answers are in the back. All worked out. All the odds are worked out at calcchat, and 63 is at calcview. Then do any of the odds 71 to 75. Their answers are in the back and they're at calcchat. Then do either 77 or 79 or both. They're at answers in the back and at calcchat. Then do any of the odds 81. Pretty exciting, huh? Just 81. Do 81. Okay? And then good idea to look at 83 and 85. They're true false. If you can figure out why they're true or false, then that would be helpful. A think about it problem is 87. An error analysis problem is 89. I sort of don't like them because they're showing you something incorrect. I'd rather you didn't look at incorrect things, but it's okay. And then exploration 91, and another think about it 93. You don't have to do those last unless you're just really intrigued and you want to pursue a little further. So I was wrong before. 2.4 is the complex number section, and because this was not required in the course description, you don't have to. You're not responsible for it. It won't be on the test, the final exam, or anywhere else. However, you may run into it sometime in a future life. Okay? So in case you do, let me go on and get out of this then. And we'll do a quick slideshow, hopefully it'll be quick, of 2.4, okay? Now, some of you may be familiar with it already, and we will see examples of it in the next section. That's why I do it now, because the book still acts like you're doing it. I'll just try to, on your test and things, not involve problems with this. But you may run into them in homework problems, so be wary of that. And I'm trying to keep talking until the PowerPoint opens, and I'm running out of things to say. It will open one of these days. Okay? I hope. All right. It's coming, I believe. I was thinking it would. Well, let's see if it's there and just not showing. There it is, okay? And let's start from the current slide. And basically, this will mostly be a slideshow, though I will do some elucidation on it. Well, this thing is so slow today. Okay, here we go. Polynomial rational functions. 2.4, complex numbers, okay? That doesn't mean they're complicated numbers. Complex has a very special meaning in mathematics. And that has to do with this thing they call the imaginary unit I. Okay, we'll use that to write complex numbers. We'll add, subtract, and multiply complex numbers. Then we'll use something called the complex conjugates to write the quotient of two complex numbers in standard form, which we'll talk about standard form earlier. And we'll not really do many complex solutions to quadratic equations, but I'll talk about them, okay? So let's get started. What in the world is this imaginary unit I? Okay? In fact, some people say imaginary numbers. It reminds me of when my wife had an employee, this is way back many, many years ago, and things like Facebook weren't even around yet. But this employee of hers couldn't focus on her job, but she was always talking about her friends. And then Karen found out after a while that a lot of her friends she didn't know. They were people she had met on the internet. So Karen would say when she'd be talking about it, she'd say, okay, is this a real friend or an imaginary friend? So sort of like, you know, this is my big rabbit Harvey. Okay, never mind. So some people have imaginary friends. Now we have imaginary numbers, and this is the imaginary unit I. What in the world is that? Well, if you remember, when we talk about things, what about this equation here? X squared plus 1 is equal to 0. What's the solution for that? What x can you plug in there, square it, add 1 to it, and get 0 as an answer? Say again? What? A negative number? Pick me a negative number. Negative 1. Negative 1 squared is? 1 plus 1 is 2, not 0. You cannot find a number that you can plug in there and make that equation true. Not in the real number system. No real solutions, we used to say. Okay? And that's absolutely true. It has no real solution because there's no real number that you can square, because the square of any real number is either going to be 0 if that real number is 0, or positive if it's anything other than 0. Positive or negative, the square will be positive. So you can't come up with a 0 or a positive number and add the 1 and get 0. It's never going to work. Okay? To overcome this deficiency, mathematicians created an expanded system of numbers using this imaginary unit I. And here's how you define I. This is, if you ever need it, this is what you need to know about I. I is the square root of negative 1. Because you see, if we were trying to solve this, what we would do is subtract 1 from both sides, right? So you have x squared equals negative 1, and immediately you say, no, you can't do that. And then you take the square root of both sides, and x would equal plus or minus the square root of negative 1, which you say you can't do. You cannot ever take the square root of a negative number in the real number system. But in the imaginary number system, when you have imaginary friends, I is that square root of negative 1. That's our imaginary unit. Here's another feature of it. Square both sides of this, you get I squared is equal to negative 1, which you can never do in the real number system. There's no number that you square it and you come up with a negative number, but in the imaginary or the complex number system, I squared is negative 1. So that's what this unit is. They say mathematicians came up with this. One in particular is, I believe it was Leonard Euler, okay? He came up with so many incredible advances to mathematics that allow you to do so many more things that his predecessors had never even thought of. One of the greatest mathematicians ever to have lived. I think we'll see a blurb on them later. By adding real numbers to real multiples of this imaginary number, we get the set of what we call complex numbers. So let's take a little time out now. That's sort of a blah, blah, blah statement. Let's take a time out. When you first started math, what were your first numbers you started with? The counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. The ones you use to count them. Now you can call them that, or you can call them the natural numbers. Both that set of numbers is given that name. Counting numbers or natural numbers. And then a little bit later, or sometime or another, you included a number you usually don't count with. 0. Now you have another set of numbers you call the whole numbers. They're all the counting numbers or the natural numbers plus 0. Okay? Those are the whole numbers. And then sometime later, you flipped over and took the negative numbers. And when you had the counting numbers, the natural numbers, 0, and their negatives, what do we call that set of numbers? They're not real yet. They are real, but integers, exactly. Those are your integers. And then at some point, probably you already had done this, you started dividing numbers, and when you divide, those are called the ratio of two numbers, so we call them the rational numbers. The ratio of any two integers is called the rational number. So now we have those. But if you have some rational numbers here, you may also have some irrational numbers. Now what do they compose of? The rational numbers, remember you can write them as the ratio of two numbers, two integers, which if you divided those, you're either going to get a terminating decimal or a repeating decimal. But irrational numbers, when you do whatever you do to them, you come up with a decimal number that never terminates and never repeats. No block of it ever repeats. Okay? That's called an irrational number. Can anyone give me an example of an irrational number? By the way, it has nothing to do with gender either. Let's say that. Okay. What would be an irrational number? Pi. Perfect example. Another? Say again? Square root of 2. Square root of 3. Square root of 5. Square root of 6. Square root of 7. Square root of 8. Square root of 9. Okay. 10, not 9. 10. Square root of 4 and square root of 9, they're rational numbers. So there's actually a whole bunch of irrational numbers out there. There's one called E. We'll talk about that a little bit later too. Okay? So we have now rational numbers and irrational numbers, and when we combine those together, what do we get? What do you want to say? Real numbers. That's all your real numbers. Every little pixel on your number line is represented by some real number. These tick marks may be your integers, but everything in between could be a rational number or an irrational number. But now we expand that and come up with the complex numbers. Complex numbers, it's a little confusing at first, but you catch it. Every complex number can be written in the standard form. A plus BI. Y'all wake up. Okay. A plus BI, where A is a real number and B is a real number. But this real number B is multiplied by that imaginary unit, square root of negative 1. That's what makes it imaginary. So this part's real, the B is real, but the BI is imaginary. Okay. So what if we had this? -5 plus the square root of -9. Can you do the square root of -9? Not in the real number system. But if you factored out a -1 and then square root of -1 times the square root of 9, what would that be? What's the square root of -1? 1? I. And what's the square root of 9?
81.
Second? Square root of 9. 3. Square root of 9. 3. Okay? Ooh, okay. So you'd have -5 plus 3i. Okay? And that's exactly what that is. -5 plus 3i. Because the square root of 9, -9, is the square root of 3 squared times the -1. I don't like the way they write this, but then you can pull out the square root, the 3, and have -5 plus 3 times the square root of -1. Square root of -1 is I. That's a long way to do it, but you can do it that way. Okay? Make sense? I'm not going to go into this in great detail. This is a little bit of nomenclature. We're not going to use it, but you might need to in the future. So, if A and B are real numbers, remember? Real number, then the number A plus BI is called a complex number. But notice this. This isn't like rational and irrational. You're either one or the other. This is more like everything's a complex number. All your real numbers, because if B was 0, all your real numbers are complex numbers. Okay? Or you can be purely imaginary and have no real component. That could be a complex number. So every number is a complex number. If you have an imaginary part, that's what we usually call complex numbers. It is said to be written in standard form if you write it this way. Real part plus or minus real times imaginary. Okay? The real number A is called the real part of the real number, and B is called the imaginary part. Now, frankly, I like to call BI the imaginary part. This book calls the real number B the imaginary part, which seems a little bizarre. When B is equal to 0, A plus BI is just a real number. When B is not equal to 0, the number A plus BI is called an imaginary number. I really don't like that either. But I see what they're saying. The number in the form BI alone, where A is equal to 0, B is not equal to 0, is called the pure imaginary number because it has no real part. Okay? A lot of blah, 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 right? All right. Now, so this is what I was describing before. Real numbers are composed of natural numbers, then whole numbers, then integers, then rational and irrational. They combine to be real numbers. Imaginary numbers are those that have imaginary parts to them. Real numbers don't have an imaginary part. And then these together are complex numbers. All real numbers are complex numbers. All imaginary numbers are complex numbers, but not all complex numbers are real numbers. So they split there. This is true because every real number can be written with B equals 0. That is, for every real number A, you can write A is equal to A plus 0i. Why would you? I don't know, but you could. It is a complex number with no imaginary part. So, now this is stuff you might need in the future. You won't need it for this course. Two complex numbers, A plus BI and C plus DI, written in standard form, real part, imaginary part with I, written in standard form, are equal to each other. A plus BI is equal to C plus DI, if and only if A is equal to C, exactly the same, and B is equal to D, exactly the same. Okay? That's the only way these two could be the same. Now, they may look different, like this may be 2 plus 7i, and this could be 4 halves plus 7i. Well, A and C are the same. They have the same value. 2 is equal to 4 halves. So they may not look alike, but they have to be the same. So what operations can we do with complex numbers? We can add or subtract them. Okay? In order to add or subtract complex numbers, you add the real parts or subtract the real parts, and you add the imaginary parts. or subtract them separately because they're different kind of. It's just like terms, right? Think of A as the real term and BI as the imaginary term. You can't combine them together by addition or subtraction, so you add A plus C, that's the real part, B plus D times I, that's the imaginary part. Difference, A minus C is the real part, B minus C, B minus D times I, that's the imaginary part. Just like you would adding like terms. You add like components, real components and imaginary components. And unfortunately, I think we've run out of time. Now, because there's nothing that we're actually going to do with this section except familiarity, we will stop right there and start with the identity later. You got your quiz. The quiz is now due 1 week from today if you can finish it in that time. That gives you Thursday a chance to ask me questions about it and hopefully turn it in the next Tuesday. Some people have already turned it in. That's fine. You can turn it in sooner as you want. If you need more time, please take it, but get it to me soon. We're running out of time. Okay? And hopefully we will finish this little section here and get started on 2.5. Get back to finding zeros of polynomials.
I didn't get a quiz.
You didn't get a quiz. Okay? Okay. Now, okay. I think several of you did quizzes. Is that right?
I just need some graph paper.
What's that?
Some graph, just a piece of graph paper.
Okay. That's easy.
Thank you.
Y'all need graph paper? Okay. Okay. Quiz. Oops. I know I got it in here. There it is. Okay, what's this? Quiz 2. Quiz 2. I know. I've got it sitting right by my computer. I've had 0 times since you gave it to me to get it done. I hope to maybe today.
Okay.
Okay. I'm on time. Good deal. Thank you.
I have a question.
Okay.
What y'all doing Thursday? We have a game.
We're continuing. We'll finish 2.4 and move on to 2.5. Okay. You got it. You ready for yours?
We got a game Thursday.
Okay. We'll do well. Okay.
Okay, thank you.
Okay. You have, oh, you're just waiting?
Yeah.
Okay. All right. So let me set it aside. You said you don't need graph paper for it. Okay. Let me, I've been